Hello and welcome back to Ikai Anant. I'm Sneha and I hope you all are doing fine with your loved ones. We are not yet done with the examples, but I promise this is the last set before we move on with the theory. In the last few videos, we did some examples of group. We did K4. We had Zn as a group. We also established GLNF and SLNF forms a group under ordinary matrix multiplication. Now going back to the very first example, if you remember, in this set we included 1 minus 1 I and minus I, right? If you missed the previous video, link will be in the description box, check them out. So this was K4 with ordinary multiplication. Now you remember in vector analysis we have I, J and K as the unit vectors they are the unit vectors in positive x, y and z directions respectively, right? And we also know that when you multiply I, J and K, you have to follow the rule where if you multiply clockwise, I multiplied by J will give you plus K, J multiplied by K will give you plus I, and K multiplied by I will give you plus J. However, reverse the direction. So if you are multiplying I with K, you will get minus J. If you are multiplying K with J, you will get minus I, and J with I, you will get minus K. So keeping these elements and these products in mind, we are ready to define the next set. Consider the elements 1 minus 1, I minus I, J minus J and K minus K, right? And the binary operation as the multiplication we discussed just now. So 1 multiplied by minus 1 will be minus I multiplied by J will be K, but if you multiply J with I, you will get minus K. So my claim is the set with this binary operation forms a group. So very first thing, you have to check whether the set with the binary operation is closed or not. So by that wheel diagram that we did just now, I know that whenever I will multiply any of the element with any other element in the set, we will get the element back, right? So closure is there. Then you have associativity, which is the property of the binary operation and hence is satisfied because multiplication is associative. Next thing is I have to pick an identity element, right? And I already told you, I think in the previous videos, that whenever the binary operation is of multiplication, find out whether your set contains 1 or not, because there is a possibility that this 1 can become your identity, and this is true here. 1 belongs to this set. Let us call this set as S for the time being, S, such that you multiply 1 with any other element x, get the element back for all x belonging to the set S. And lastly, inverses. So for inverses, find out the inverse of each element separately. What is an inverse? If you multiply x, any element of S with another element y in S, you should get 1 back. Writing the inverses of the element here only. If you multiply 1 by 1, you will get 1, and hence 1 is a self-inverse element. Always remember that identity is self-inverse. Identity is self-inverse. This is true for every set with binary operation which forms a group. If you have an identity, it is a self-inverse. Now if you multiply minus 1 with minus 1, you will get plus 1, and hence the inverse of minus 1 is minus 1. So you have another self-inverse element in the set S, which is minus 1. Now if you multiply I with minus I, you will get plus 1, or vice versa. Therefore I and minus I are inverse of each other. Similarly, J multiplied by minus J will give you 1, and minus J multiplied by J will give you 1. So they are inverses of each other, and likewise for K and minus K. And hence this set with the binary operation forms a group. This group has a very special name known as, this group is denoted by Q8 as it is written here, and this is known as quaternion group. Quaternion group. This was the next example, quaternion group denoted by Q8. It has 8 elements and the binary operation is ordinary multiplication. Moving on to the next one. So before I actually introduce this group, I would like you to consider a hypothetical situation where you bumped into somebody who knows that you are a math student and tries to test you by giving you a number, say 10, and ask you to tell about the number. So least of least you would start by saying that okay is an even number, right? Basically layered or divisible by 2. Then the next point you would say that okay, it's not a prime, it's a composite number, so it can be factorized in prime factors. So 2 and 5 will be the factors. Then you will say I can get the factors of 10, or I can tell you that 1, 2, 5 and 10, these are the only numbers that can divide the number 10. So basically if such kind of abstract question is there, it is up to you to move the interview or move the test to the direction that you want, right? And lastly, when you know that 1, 2, 5, 10 are the numbers that divides 10 completely, you also know that there are numbers that have common factors. So for example, you have 4 and 10, they have common factors as 2. You have 6, the common factor, right? And you have 8 also. 8 and 10 have common factors like this. And lastly, you are left with the numbers that are less than 10, which are co-prime to 10. So you have 1, we consider 1 as co-prime to 10, and then you have 3, then you have 7, and then you have 9. These are the numbers that are co-prime to the number 10. And I want you to consider this consider this scenario where you have a number and you find out the numbers that are co-prime to the given number, or the numbers that have no common factor whatsoever with your given number. Right? With the help of these numbers and this set, we make our next group. So given any number, you can always talk about these properties. You can categorize it as even or odd, composite or prime. You can find out the factors. You can also say that there are numbers which do not completely divide 10, but they have common factors. And then you have the set where the numbers are co-prime to your given number, right? So when you collect the numbers, collect all the positive integers such that the x is less than n and they are co-prime to n, that means GCD of x and n is 1, you basically form Euler's group denoted by UN. Well, we have to show that this is a group, but yeah, the name of this group is Euler's group, and the binary operation here is the multiplication modulo n. So what is A? Multiplication modulo NB is equivalent to R, where what is R? When you when you divide A multiplied by B, the ordinary multiplication, by n, you will get some remainder. By division algorithm, the remainder is 0, or it lies between R and n, and this remainder will be your answer. So this is the contemporary version of addition modulo n. In addition modulo n, we add the numbers and then we divide it by n to get the remainder. In multiplication modulo n, we multiply the number divided by n to get the remainder, right? This is known as Euler's group. Now for different values of n, the group is different. So for example, for u, if I talk about u2, the set will contain only 1. If we talk about u3, the set will contain 1 and 2. Similarly u4, so we are basically collecting all the numbers that are co-prime to 4, so 1 and 3 only. Then you have u5, since it's a prime number, every number which is less than 5 will be co-prime to 5, right? And so on. So if you have to check whether this is a group or not, one method is the classical one, where you just show that closure property hold with the help of multiplication modulo n, and associativity is there with this binary operation. You find out the identity, and then when you have to find out the inverses, you have to think about each and every element for each and every n, right? So in order to avoid all these calculations, we have Kelly's table with us.